Thank you very much, Siert. Indeed, geothermal, but a bit different concept. So what we are very much interested in is understanding the geothermal motor. And I leave it to the colleagues at the service to transport it anywhere. But to find something that is viable, you need to be looking at a broader picture. And we have already seen the bigger picture. We have seen some very local systems. And one of the things that we increasingly try to do is actually bring those different concepts over different scales together. So really look at a geothermal motor from the source to the surface, and understanding not only why it is there and how we can take it out, but also where it's coming from and what the source is, and use that in understanding what you're looking at. So, well, this was just a very quick definition about what is indeed subsurface energy, which is relatively in the shallow space, where you can also actually store your energy. That was, Janos already mentioned it. I will focus at this moment only on the deeper geothermal parts. So we are basically moving into the domain, and I've put it here between 2,000 to 3,000 meters, which is quite a common depth. I will talk a bit later about the Dutch case, where, well, Bernard already said, let's talk to Mark about the potential in the Netherlands. It's not so bad compared to the rest of Europe. We are, I would not say we are in a hotspot, but it's also not very cold. But we have not such favorable conditions, which sometimes turn things a bit upside down. So I will talk a bit about different ranges, from very shallow but very hot systems to the deeper ones and anything in between. I will be talking about two different systems. So we have the hydrothermal system, where you really have a heat source. Think about all kind of Pannonian Basin with hot gradients, strong gradients, hot heat very close to the surface. I will show a few cases about that. I will talk also about the hot sedimentary aquifers like Vienna is, but also for the Netherlands, where you look at a completely different system with different requirements, different options for geothermal energy. And what works in one doesn't work necessarily for the other one. So geothermal is not just a plug and play and just do everything in the same way. It really requires different perspectives and understanding of what you're looking at and what you would like to get out. Now, this was indeed a bit of road tripping in observational seismology. I will talk you through a few. I see Botswana is missing. I will say a few words about Botswana, then go on a very presently active project that we're doing in Kenya, really monitoring a geothermal field, somewhat similar to what we are going to do here also. But we also look in Botswana, which was more on a regional scale, which is another picture of what we are going to do here, looking for Siert's favorite baby plumes under the Balaton High. But I will also talk a bit about the Netherlands to show what kind of perspective we have there and what kind of new methodologies we are developing to actually explore geothermal possibilities in relatively unfavorable conditions. So the first two parts are in an area that is, well, basically like Hungary, like Indonesia, like New Zealand, very favorable place. We are in a strong rifting area in the East African Rift Zone. A hotspot for geothermal, often coming very close to the surface, 300 degrees almost when you put your finger into the ground. Ideal conditions. We kick off at the bottom in the southern part of the East African Rift System, and particularly going to the larger scale. Implications for geothermal on larger scale rifting systems, and how imaging the subsurface can actually change your perspective quite a bit on what the potential might be, but also what the impacts might be for a society. Because in general, it's assumed that in the Okavango Delta, it's basically the terminus of the East African Rift System. It just stops there. You have the last hiccups of geothermal activity, high gradients, some evidence for melt in the upper mantle. But we have been running a deployment there, a nationwide deployment in Botswana. So you see there we had a deployment with relatively large station spacings of, I think the closest was 75 kilometers up to 150 or even more. So large spacings, very large area, really looking into upper mantle, lower mantle kind of imaging. It is a very dynamic area because it is at the end of the East African Rift System. You have a lot of evidence there. There are lots of cratons. There are all kind of mobile belts in between. So we see the evidence of past and present dynamic activity. And we also see that there's very strong variation in sediment thickness. So there is all kind of things going up and down there. It's filling up. And this has been happening in the past. So all kind of indications that this area, although in the middle of the craton, still is at the terminus of the East African Rift System, quite experiencing a lot of activity. And then suddenly we had basically our instrument running together with Utrecht University. So we combined the two data pools at that moment. Now everything has been transferred to Twente University. But we just extended our project with a few months, and we were incredibly lucky because one of the largest intraplate earthquakes in Africa in decades happened at that moment in the last months of our deployment, magnitude 6.5, at a completely unexpected location because it was happening somewhere there in the middle, in between the cratons, far away from the East African Rift System, where you would expect maybe a magnitude 6, 6.5 at maximum. And we thought, like, what is that doing there? So we focused a bit more with our tomography on this area, and we see very clearly on the different depth levels. We see it's in a sediment basin, so it is a bit of an history, possibly of an extensional area. Not that we directly focused on that, but we saw that already. It's a border between the craton, on the border of the craton and the mobile belt. But if you go a bit deeper, you see it is nicely embedded in between the cratons, and it's actually on the border. So this didn't really help a lot yet. So we started looking at some of the transects. So we looked at the transect from north to south to capture those elements that we are familiar with. We already had a hint here that what we will be looking for. So we will look like, okay, East African Rift System might have an impact on this massive big intraplate earthquake. So you see in on the left side in the tomographic image, you see the southwestern branch ending of the East African Rift System. Clearly the lower velocities indicating, in this case, warmer materials. And you see the Kaap Vaal craton, very old, cold, very fast lithosphere on the right-hand side. In between, remnants of cratons and mobile belts. And what is actually interesting was that we see basically a progression from that East African Rift plop, going a bit upward, traveling underneath a fragment of one of the cratons. And we see that the earthquake just happened directly in one of those fingers pointing from that blob from the East African Rift System all the way till the source of that earthquake and a bit further. So we were suddenly interpreting this in a somewhat different way. We have done many more studies, of which I will not completely bore you to death today, but the main importance is that we believe now with this new information that the extension of the African Rift possibly extends actually 600 kilometers more south than it was previously thought to be. Now this is of course not only interesting so we can explain the earthquake, but it has massive geodynamical consequences potentially if we now suddenly need to do all our stress fields with an extension of that whole dynamic region 600 kilometers more south than it was before. And in terms of geothermal, it might actually be very interesting to explore this as well, because this is actually relatively close to the capital Gaborone. So there might be some options that we suddenly get a new picture on the geothermal potential for Botswana, which was only considered to be happening in the north mostly. So that was the broad scale. The next project, we moved a bit more north, and we moved to Kenya. And in the middle of the East African Rift Zone. And we were there running a deployment on a very small scale in one of the largest geothermal production fields in Kenya, in Olkaria. And this was really meant to be monitoring the geothermal motor. So the field there is quite an active one. It's in the middle here of this branch of the East African Rift. There is a lot of, actually a Hell Gate spark national park in which it is located. Now you can imagine where the term Hell's Gate comes from. And you see there all the steam with the giraffes, the lions walking through it. It's quite an interesting place. If you ever would like to do a nice trip to a geothermal area, this is my favorite one. But what you also see there is that we installed a lot of seismic stations on a relatively short distance away from each other. And we basically could monitor the whole flow and injection part of the area that was running in one part that was already active and another part that became active during the deployment phase. So they were test drilling already, but it was not fully operational yet. So we actually have a data set that shows what it was before and what it is doing right now. And they have extended the network, so they keep on monitoring at this moment in that area. We could also progress a bit faster because we had modern seismometers, so it doesn't need so much infrastructure anymore. Normally you would have to build a vault and a housing and this and that and such and so. It took forever. These are seismometers. You just dig a hole, you drill a bit deeper, you toss the seismometer in, and you bury it and you're done. You walk off. Put a solar panel on top and you're done. So it's relatively quick and makes it much easier to operate. So this brings especially broadband seismology a bit closer to an operational kind of phase. So the area that we have is the following. So this is the whole area. We see the kilometers over there. The stations are like 4, 5, 6 kilometers maximum away from each other. There runs a big gorge in the green colors through the area. The top left part has been already fully operational for decades. The lower part on the more orange colors became operational during our phase. So we have been doing here all kind of seismological processing. One of them was ambient noise. So we look at dispersion curves which indicate what happens between two stations on different frequencies, sampling the shallow, sampling more deeper, and through an inversion process, we can then build a whole model. And that we try to link back to the geothermal motor concept. So can we actually see the behavior of this geothermal motor, including the sources that are coming from beneath? And that's the advantage of this broadband seismometers in a somewhat bigger network, that you might lose detail on the shallow parts, but you can see a link to the actual source of where it's coming from. And that gives you a picture like this. So on the left side, you see a picture that we have contoured on several velocity intervals. So we see parts that are very slow, we see parts that are very fast, indicating, in this case, somewhat that is more cool or that is more warm. And what we clearly see is these magmatic body intrusives. We see them at the bottom coming up as fingers, and we see the different layers in the reservoirs in the part in between. We also see the cap rock on top. So if you now carefully look at this image, you actually see all the elements of this structural geothermal motor concept. You see that coming back in the geothermal imaging. Now, what we are going to do here is basically a bit similar, but we will fill it up with nodals. So looking at higher frequencies, decreasing the spacing in between, so that we do not only get the bigger picture on the full concept, including the source, but we also can fill in more detail what is happening in between. And then some options that we run into quite recently. And we're looking more for geothermal options in an aquifer setting. So this is not necessarily very hot. It doesn't have massive magma coming up. So you're looking at geothermal gradients that are much more in line with what you find in the Vienna Basin, for example. So you look at mostly low to average temperatures. Worst case, 30 degrees up to 150 maximum. Much higher you do not get. In mostly porous layers in depth ranges of 1 to 4 kilometers. The water circulates between two boreholes, a doublet, mostly under pressure, sometimes a bit too much pressure, and we know that this could create earthquakes. So this is often a problem, especially if you come into more densely populated areas in Europe. And the temperatures are basically only making it suitable for heating purposes because you cannot create any electricity out of these temperatures. But they require very specific conditions to have enough heat and avoid problems. Because in these cases, you would not like to start pumping, and in the Netherlands it's even strictly forbidden. You cannot start pumping through a fault system. So you need to find your way through the different faults and find a place where you can actually start pumping that is not going through a fault. If you're also in an aquifer setting, and particularly in the Netherlands as well, and I will show you an example later on from one of the seismic lines with borehole information, it are very intermittent layers. So you have beautiful sand layers with maybe a little bit of conglomerate, but mostly some sand, coarser sand, finer sands, and then suddenly there is some clay in between. And these clays are very annoying because they're cutting through all the time, and if they become big enough, they significantly slow down your capacity to flow from one side of your doublet to the other side. So you either need to then start increasing your pumping with increased risk of earthquakes, or you just don't reach the capacity that you're looking for. So under these conditions, we have been trying to explore what is actually now what we can do, because the government of the Netherlands has basically declared 80% of the Netherlands as unknown or very low potential for geothermal. And that's only because they're looking at these preferential conditions where you have these sandstone layers that are continuous, that are large, that are thick, and where they can pump over a few kilometers distance and they can produce something like 25 megawatts or more. Anything else is not considered to be useful. But we also see that delivers a massive amount of energy that is not always being used. So 98% or even 99% plus goes into the tomatoes, the water bombs, and only less than 1% is being used for heating of houses. So there is some industrial heating, lots of agriculture, but houses, very, very little. So we're looking at what can we now actually do, because in many places in the Netherlands we have those sand layers, but they are often at different depths or less continuous, they are less thick, or they suffer from these clay lenses in between. And for that, one of the things that has come up over the years in the Netherlands, it's by Geothermal Group Netherlands, has developed a new concept, what they nicknamed the low unit cost. It's widely applicable, but can be very locally used. And it's a solution for regions that are outside the traditional potential that is often seen on the 25 megawatt concept. So what it is doing is, and I see there are still some Dutch things on there, but I couldn't change the figure anymore, is that it has a few advantages. Because what you will do is that you first drill an exploration hole, and there because you will be extracting water around your exploration hole, you can already do a test if it is actually working or not, or if it is bone dry, or that it has sufficient porosity, permeability, and presence of water. Only then you will drill actually the blue and the red one for the injection and the extraction wells, but they will be done in a completely different way. So instead of just having 2 points kilometers apart from each other, you now put in basically 2 drainage pipes that are somewhat parallel to each other, but it can be under any angle to fit the local geometry of your sandstone layer, so you can avoid these bigger clay lenses in between. And you basically get a flow going, not between points, but more in a kind of a plane, in between the sandstone layer that you're looking for. They're only a few hundred meters apart, so lower pressures, but you also, of course, have lower production. This is typically very suitable if you would like to create geothermal heat very close to the area where you would like to deliver it. So in the Netherlands, the government has a philosophy to put quarters of cities, quarter by quarter, they go off the natural gas and they go onto the heat networks. And that you can actually then do very nicely, because these kind of systems typically deliver like 65, 75 maximum degrees. It can serve 600 to maybe 1,000 households, and that's about it. So do not expect to heat a whole city with this, but a part of a city, yes. But if you do this for a few of them in a row, you also have a nice redundancy in your network that if one pump falls out, you still have 8 or 9 or 10 in your network that are still functional. So you're also less dependent on the malfunctioning of that single big doublet that if that falls away, you lost 25 megawatts, and then you need to find a solution. So, and these things are relatively small, so you can fit it under 10 parking spots or in a shopping area or under a park. They can be under the ground, they don't need to be above the surface. So this is a concept that could actually very nicely work if you would like to do 600 houses, get like 63 degrees up and put something in 33 to 45 degrees down. So the production and injection are under low pressure, so it is ideal for the energy transition to actually have a local provision of heat with low transport costs, little loss of temperature in the transport of your material, so it can also come out a bit lower. And if you mix this with the energy that you already have from incinerators at a high temperature, then it's very easily to mix it in and provide a very stable flow. And in case you need to go a bit up, you put a little heat pump up and you pump it up to above 70 degrees or whatever you would like to get. So it is really a neighborhood transition concept that is possible. This allows also, because you're going also potentially to lower temperatures, that we do not necessarily need to go to 2.5 or 3 kilometers. With the geothermal gradient that we have in parts of the Twente area where we are coming from, we can actually go to 1800, 1900 meters, get something up like 65 to 73 degrees, but immediately provide it to the local neighborhood. But it's much more shallow than what is in the nota for the Dutch energy geothermal provision. So we thereby suddenly open up for a much broader application with a very local supply chain for geothermal energy. And this is then what you will need to do. And well, Siet was very enthusiastic saying that most of the Netherlands is covered with 3D seismics. Unfortunately not. There are certain parts that are massively oversampled. There are also lots of parts that have only the 2D lines, and Bernard already indicated that 2D lines can be dangerous. This is some of the analysis that we have done for an area that was a former gas exploration area. And we're looking for these layers, but you already see in the borehole information for this sandstone layer that there are lots of variation in this supposedly sandstone layer with all kind of intermediate compositions that actually prevent a continuous flow potentially through your geothermal reservoir concept. So with this kind of information and this detailed analysis, but also with the capacity to do this over much smaller distances, so you can actually lean on a more 2D concept because you do not require to go kilometers away from your line. You stay relatively close to your line, and thereby, even with little information available, you run much less risk because this whole concept of a test drill is about 1 million. Setting up the whole system about 8 million. Very different from the 35 to 40 million that a big doublet would cost. If you go deeper, it would even be more expensive. So it is a much easier concept to apply, and especially if you bring this close to urban areas. So this is then the concept of the Netherlands. So our university is there at the yellow word with the arrow, Enschede. You see we have a lot of these faults coming together there. But with this concept, so there would be no way that we fit in a 5-kilometer doublet structure in this one. But if we would put in only something that is maybe 500, 600, 700 meters apart from each other, we suddenly have space. And we have the temperatures that are sufficient. So suddenly this whole area, which was unknown potential or very low potential, suddenly becomes an area that has very high potential. And we are actually working on a project right now to actually get one of those concepts tested in this area, together also with industry, public-private partners, to see how this now really works, and if we can also, in this concept, with this flow over a plane, if we can understand the geothermal motor concept fully well. Is there any earthquake risk in this? Well, the production in the Netherlands is relatively shallow. So that helps, well, if you have an earthquake, you're more in trouble. But it helps because your corrosive permeability tends to be a bit higher. With this system, we actually go over low pressure, low temperature systems, and we pretty much do everything in sandstones, not in carbonate formations. So that has very positive consequences. If you look at a slide from Buijse et al., you see that the orange colors are sandstones. And this is about a global study of earthquakes in geothermal sedimentary reservoirs in relation to the geology. So you see that in carbonates and with the larger depths, you get quite a lot of earthquakes on the left bottom side. But we are staying all the way up on the top right side in the sandstones. So even on the global doublet system, there is very little chance of earthquakes on this concept. And with this lower pressure, lower conditions, you have much less chance. So we believe that this is an almost risk-free, well, that's a harsh word, but it will contain very little risk on bigger earthquakes that might be a problem. So then we will, a few words, Esther already indicated it, we will start a project this year with HUN-REN and the HUN-REN, I miss an N there, University of Twente, but also partners. We look into the geothermal concept and the mini plumes or the baby plumes. There will be 20 broadband seismometers, and we will fill that up with nodes in between. 3 PhD students on it, so still in the coming years, ample opportunities to have them present and show what we are actually gaining on this information. What we are particularly going to do there is merging traditional seismological tools plus the groundwater modeling techniques, so understand better where the whole flow part goes, because so far in our seismological studies we have never considered that. We see patterns, but we have never done anything with it. And we would like to go to multi-observable thermochemical tomography, so we will not only look at one parameter, we will try to put everything together that we have for a whole area. So that means that we try to get multi-parameter consistent models, multi-observable consistent models that will actually give you composition, that will allow for flow modeling, but also gives you information on your heat flow and your temperatures. So by that we hope to get much more insight and understanding and control of what we are doing. So in summary, we believe that by using these techniques, we can actually retrieve information on geothermal systems at different scales, starting from very broad and the sources where it's all coming from, all the way till the local understanding of the geothermal motor. Provide unique insight into the heat processes and details on geodynamics and composition. And with these new concepts and this more detailed monitoring, we can provide opportunity for much more local applications. And yeah, we're looking forward to kick off the next phase here with the colleagues in Hungary. Thank you very much.
Thanks a lot, Mark. I think you presented a lot of novel approaches and also some very smart solutions to issues, let's say, where you make an advantage out of a disadvantage. And I think this is the creativity that we need. Questions or comments from the audience? Yes, please.
Thank you for the presentation. It was great. And my name is HUN-REN, representing. Oh, all right. I think I don't need it. Do I? That's right. Thank you. I'm really interested to understand the flow rate, what we could achieve, because speaking of touch time, this Permian, we generally have a very low porosity. So having some kind of experience in the North Sea, nobody really likes it, so nobody really produces it. When I saw that you have about 20% porosity, that was a little bit surprise for me. So thank you.
Yes. Well, it's highly variable. So the information that we looked into now is an onshore part. It's a shallow, much more shallow reservoir than what is in the North Sea. So it's much more higher up. And there has been on previous boreholes in the area, they have done porosity and permeability studies, which I have to admit, they vary. So they're absolutely not consistent, and that's also why so far people have been a bit hesitant to move in there. But there is a significant amount of the cores and the samples that have been analyzed for porosity and permeability that actually give perfectly suitable values for geothermal exploration. And this is one of the things that we are at this moment exploring. So we have been scanning some of those boreholes to get a better understanding on the composition. We have a massive multispectral, hyperspectral borehole scan facility in the University of Twente, where we have been trying to link the spectral information to the porosity and permeability information, particularly focusing on clay particles, both as layers as well as infill in the pores, to understand if we see this relationship. And that actually is also of interest for operators, because the more loose material you have in your pores, the more problems you get on your pumps and pipes in the end. So, no, we don't have any flow rate numbers yet. Well, that is one of the things that we hope to go test, yes.
Final question for Mark. Yes, Gabor.
Then I lost the name. Where is my local team? Help. Dani, Esther. Yes? Glad that you heard it, because I could not repeat the name right now, but